we have been running around talking about vector space and stuff. And we also have been talking about metrics a lot as well. So in this lecture, we'll actually get to see how these two things kind of relate to each other. Let me actually begin by looking the example down here. I'd like to find the basis for the row space and the null space of this matrix. Note that my matrix A, this is a 4 by 3 matrix, so it has 4 columns. It has 4 rows and it has 3 columns. So let me start by talking about a row space. A row space of a matrix is actually pretty simple. I just took the row of a matrix and then use that as a vector. So I'm gonna view each of the rows of A as a separate vector, and I'm gonna use that to span a vector space. So the row space of a matrix A here is gonna be just the span of the 4 vectors that we see. So it's gonna be 1, 2, and 3, 4, 5, and 6, 7, 8, and 9, and then 10, 11, and 12. Okay. So I'm gonna use rows of A to span the vector space, and that is called a row space. So the idea is actually pretty simple. And we actually already have seen something like this. Well, for this number, this is actually just the number that we see from example 5.3 in the previous lecture. And we actually knew already that the basis for the span of these vectors are actually gonna be just 1, 2, 3. And 4, 5, 6. Okay, but for now, let me actually show you another way to find the basis for the span of this 4 vector here. Another thing that I can do with the matrix A is that I can actually just go ahead and row reduce this matrix A. Row reduce. On second thought, I think row reduce doesn't have a hyphen, so row reduce. Well, if you think about it, the operations that we do when we row reduce a matrix, be it exchange the row, be it change the order of the row, be it multiply by scalar, and be it add multiple of a row to another, these three operations actually have no effect on the linear independency of the vector, and it also doesn't change the affect the basis of a vector space. So if I were to row reduce this this matrix A here, the row that I'm gonna end up seeing are gonna span the same vector space I see earlier. So let me actually just go ahead and write down the reduced row echelon form for this guy. I'm gonna see 1, 0, -1, 0, 1, 2, and then 0, 0, 0, and then 0, 0, 0. Voila! So what I'm saying is these 4 vectors here would span the row, would actually span the space that's spanned by the original 4 rows of A. In other words, well, 0, 0, 0, it doesn't really span anything. In other words, the first 2 rows that I see, this is gonna form the basis for my vector space. So when I do the when I reduce the row of A, when I do the reduced row echelon form, only the row that has a leading one is gonna be the basis for my row space here. In other words, my basis for this space is gonna be just 1, 0, -1, and 0, 1, 2. Notice how this is not the choice of basis that we see earlier. And that's because, like I said earlier, the number of bases, which is the dimension, are going to be fixed, but there are many different choices for the bases. Speaking of dimension, so this space is going to have dimension 2. So let me actually kind of write that down. Dimension 2. Okay, so that's for the row space of a matrix. Now, let me talk about the null space. The null space of a matrix are basically the vector that when we multiply to this matrix, so it's going to be the set, not the vector, it's going to be the set of variable. So I have my matrix A here, and I multiply, so it's going to be, it's a set of vectors, yeah. So the null space of a matrix is a set of vectors that when you multiply that vectors with A, you're going to get a zero vector coming out. And because the dimension of my A is 4 by 3, so my variable vector here is going to be x1, x2, and x3. So, the solution space for this matrix equation is going to be my null space. It's going to be my null space. Whatever matrix, whatever vector that when I multiply that by matrix A and get 0 coming out, that is going to belong to my null space. So, to find the null space of a matrix A, I'm just going to need to solve this matrix equation. And like I always do, I'm going to write the augmented matrix form for this guy. So that's going to be 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, and then 0, 0, 0, 0. Okay, now. I'll just have to find the reduced row echelon form for this guy. But well, nice thing happened to nice people because I actually already find the row reduced form for the matrix A. And note that my right hand side here is actually all 0. So when I do the row reduce, my right hand side here will not do anything to my row reduced form. Let me actually also recall that when the right hand side are all 0, this is called the homogeneous equation. And whenever we deal with the homogeneous equation, the set of solutions to that is going to automatically be a vector space. So if I were to row reduce this guy, it's going to be just the same vector that we see before. Same matrix that we see before. 1, 0, negative 1, 0, 1, 2, and then 0, 0, 0, 0, 0, 0. And then my right hand side is going to be just all 0. Okay. So, I have a free variable here and the set of solution that I'm going to see. It's going to be my x3 is free. My x1 is going to be the same as x3. And my x2 is going to be negative 2x3. This guy is just x3 times 1, negative 2, and 1. So the basis for my null space here, the basis is going to be 1, negative 2, and 1. Okay, now, there is one thing, there is actually two things that I'd like to point out. Notice that the basis for the null space is going to be orthogonal to the basis for the row space. If you do the dot product of these two guys, let me actually do that. So if I were to do the dot product 1, 0, negative 1, and 1, negative 2, and 1, the dot product is going to be 0. And the same thing, if I took the second basis, 0, 1, 2, and I dot product that with 1, negative 2, and 1, this guy is going to be 0. So, the basis for the row space and the basis for the null space is going to be orthogonal to each other. The second thing that I like to point out is that the dimension of my null space here is 1. So null space has dimension 1. Okay. So, if I add the dimension of the row space with the dimension of the null space, so I add 2, 2, 1, I'm gonna get a tree. This tree here is gonna be the number of elements in my row space. So in other words, the dimension of the row space is 2, the dimension of my null space is 3, and 3 is the number of columns of my matrix A. It's the number of elements in the row of A. So we're gonna come back to this in a moment, but let me go on to the other example.